Good afternoon and good morning, depending on where you're joining us from today. And welcome to our electric aircraft ducted fan design webinar today, presented by Maya HTT and Softenway Incorporated. So we're going to go ahead and get started. And once again, thank you for joining us today. So my name is David Stevens. I'm a technical pre-sales engineer at Maya HTT, and I'm joined by Sasha Podlick of Softenway. A little bit about myself. I'm a technical pre-sales engineer at Maya, as I said. I have about 7 years of industry experience in CFD and turbo machinery analysis before I joined Maya a few years ago. And I'll go ahead and let Sasha introduce himself.
Yeah, hello everyone. My name is Sasha Podlick. I'm an application engineer at Softenway and have about 4 years of engineering experience in turbo machinery in general, but also CFD and thermodynamic cycle analyses. Yes.
All right. So next thing we'll do, we're just going to go ahead and do a quick intro of Maya, if you're not familiar with Maya, and as well for Softenway, if you're not familiar with Softenway. It's a little bit about Maya. We're an engineering company, software services, etc., with about 250 employees with a global presence. We are Siemens VAR, and we have about 15 Siemens portfolios. We also develop over 30 of the Siemens products, so we're also an OEM for Siemens products. We also have a large services division where we have completed over 1,200 projects for customers across the globe. We also, we're a full engineering company with software services, whether it's, looking today at simulation for anything from, PLM as well to even AI, IoT these days. I'll go ahead and hand it over to Sasha.
Yep, thank you, David. Yeah, Softenway, a little bit about Softenway. Softenway is a global R&D engineering company with specialization in the development of efficient turbo machines. And we're headquartered in Burlington, Massachusetts. It's a little bit north of Boston, here in Massachusetts. We are supporting over 600 customers worldwide, that can reach from industry-leading OEMs, but also startups we're supporting. Currently, we have around 90 employees in global offices so that we can support our clients and customers 24/7. And we have vast experience in advanced turbo machinery, R&D, but also critical CO2 cycle and clean technologies, as well as machine learning and AI products. We completed more than 200 consulting projects, so we're not simply offering software, we're also a consulting company, and also ISO certified. Okay. A little bit of the Softenway portfolio, the Axstream software platform. That what we're talking about today is just a fraction of what we offer. Is the turbo machinery design, which you can see in the middle, which include generative design, 1D, 2D, and 3D turbo machinery design analyses, and some rotordynamics and bearing calculation. But we also can go beyond that with system simulation from the 0D to the 1D level, so we can create all kinds of thermodynamic cycles and systems with a different package. And we have some AI and machine learning products, as I mentioned already, to combine the various systems and component design aspects. All right.
All right, so with that, one thing we would like to do today as we do these webinars is we'd like to take a few polls just to help us get to better know you, understand your needs, and how we can focus our talk today. So we'll go started with our first poll today. Is what is your primary interest in today's webinar? So we'll be talking mainly about ducted fans today and turbo machinery design in that space. But certainly a lot that can apply here today goes across the spectrum in other turbo machinery design disciplines as well. But as like I said, we'd like to know a little bit more about what you came to see here today. All right, we'll go ahead and close that poll. share our results. Okey doke. So it looks like, yeah, really that we have a bunch of people here for, the electric aircraft propulsion work specifically, but also a large amount as well for really just turbo machinery, CFD, aerodynamics analysis, and design workflow. So that's great. We're happy to see that today. So that being said, our webinar today is on ducted electric fans for aircraft propulsion. And as you can see, this is a process, or I should say an industry with huge growth projected and huge growth over the last couple of years. So we thought this was a great way to spotlight the technology for turbo machinery analysis, and also maybe help people who are getting into this space get an idea of what we need to do in order to start some of their designs. And this is like I said, an area with very large growth. Anywhere from small startups to large companies like GE and Rolls-Royce are operating this space, to develop full hybrid technologies as well as full electric technologies. So electric ducted fan, we can see that here. We're going from, instead of a traditional gas turbine, where we're burning jet fuel or something like that, to produce thrust with a fan configuration. In this case, we're being driven by an electric motor. And really what we're talking about today is simulation-driven design. Everything we're talking about today is we're talking about doing simulation in order to speed up our design process, speed up our time to market. A lot of us are probably aware lately, if you work in this simulation space or in this industry, that there's a lot of competition. There's a lot of pressure to get things to market quickly, and certainly doing simulation up front is designed to make that happen. We don't want to be finding defects when we're doing our prototypes. We want to be finding this stuff during simulation. So as we can see here, the ease of change is easy at the beginning and more expensive as things develop later on. But one thing that we want to highlight here today is that you can still do simulation, generate a design and do it early in the design phase, but we also need it to be efficient. So you can also push out and get in a loop of not really getting where you need to go if you don't have design efficiency and efficient simulation tools. So today we'll be covering a ducted fan design workflow for the turbo machinery inside a ducted fan. So primarily that turbo machinery section, and that workflow is shown here. Starts with Axstream using their tools, and then goes over to using StarCCM Plus to do a full analysis of the performance. From there, we can gain insights that maybe we want to feed back into Axstream and do another iteration. And we'll show that clean workflow today, where we can take iterations, start with a design and a templated workflow, use the output from Axstream in StarCCM, and then likewise that could go through a loop very efficiently and reduce rework. So we chose a case study on this, our electric ducted fan case study here, for aircraft performance. We're trying to hit a cruise speed or probably a top speed of 190 knots, which is fairly lofty, but we're trying to get some places here. On our electric motor side, we're looking at electric motor, for this case of around 200 kilowatts. We have some rough dimensions there, the space that it needs to fit in, as well as an operating speed of 5,000 RPMs. And really the performance targets we'd like to hit for this, for a preliminary design, or a total efficiency of over 90% and a gross thrust of over 400 kilonewtons, or excuse me, 4.2 kilonewtons. And with that, we'll jump into our next poll. And we'll go ahead and do our next poll, which is, do you currently have a tool in place for performing turbo machinery aerodynamic design? If so, what is it? Do you currently have a need for a tool? Possibly we can help you out with that. So far, it looks like about a vast majority have a commercial solution in place, which is great. And then today, we'd really like to show you a very clean workflow in that commercial space. This today is showing StarCCM Plus. we go ahead and see our results here. And yeah, of course, we're looking at, most people have a commercial solution in place, but also use some of us, use a custom in-house solution. One thing that our companies can do is help you, improve those solutions possibly if you're not using a commercial solution, or maybe, improve a commercial solution that you already have and streamline that approach, are all things that we can do and do here at Maya as well as Softenway. With that, I'll turn it over to my colleague Sasha, who will focus on the ACStream portion of our presentation today.
All right, yeah, thank you, David. As David said, I will give you a short intro into what ACStream can offer, what's the plan to use ACStream in this workflow. And I already mentioned that we can use it for 1D and generative design, and that's exactly what we're talking about today. You can see here just one slide about the preliminary design. So the generative design methods we have inside ACStream, where you can use just a few input parameters that could be boundary conditions or that are actually boundary conditions, but also some geometrical constraints you might have. And all these information come from the system level, and some constraints in diameters, for example, it's basically your choice as well, and then certain requirements. With these information or with these input parameters, we can generate a vast design space. You can see that in the middle with the various dots, and every point is a different geometry generated. And so we get a first initial geometry we can then further analyze in the next steps. I will show that in a second. But the core idea here is to generate thousands of designs in a very short amount of time, within seconds. Okay. So the next step is then, when we have our initial design, we have applied some filters and narrowed down our search, and we have a design selected, we would go into the 1D and 2D streamline calculation. Here we can evaluate any operating point, be it design or even off design, with the meanline solver or a streamline solver. And for the streamline, you can see that there's on that blade, there's some lines, some horizontal lines that are the span-wise sections we can insert, and to generate more accurate results. For that, we can use the streamline 2D calculations. We can then also change the geometry in this step to accommodate for other certain requirements we might have. We can check Mollier diagrams as well as velocity triangles, and get also an insight in certain losses and how the machine performs. We can see here, like Mach distribution contour, for example. We can see there's some transonic region, so we can consider that in our later blade design, for example. Okay. Then I said in the subsequent blade design, we are coming to the profiler and the actual blade designer. And here we can adjust our blade on each span-wise section. So we have various profiles on each section, and we can change the inlet angle, outlet angle, stereo angle, you name it, the thickness distribution, and so on. We can apply twist factors as well. We can apply, or there are some extra features inside the blade profiler which allows us to facilitate the design. So what I mean by that is we can, for example, smooth or apply smoothing from hub to tip, so that we can make sure that we get a nice smooth blade. But you also can import existing profiles. So if your company has some go-to profiles that would like to use, we can import these and can be used in here as well. And then the final step, when we have done our profile design, we can also then export to the various formats, be it for structural FEA calculations, or as we will later see, for CFD, 3D CFD calculations. All right. And then what we also can do within ACStream FlowPath is with the tool AxMap, we can run parametric studies, for example, or create performance maps. That can be done by using the 1D or 2D Streamline Solver. That is totally up to you, to your choice. And as I said, we can basically run it in 2 operating modes. First one is design mode, where I can run parametric studies, for example, can see the effect of my stagger angle of the blade or hub diameter, you name it, and then the effect on the performance. The second mode is the analysis mode, where we could create simple performance maps. So pressure ratio and master rate, for example, can be plotted then as well. These maps can then be saved and then can also be used then for system modeling later on, and gives you a first and fast insight in how the machine will perform in off-design conditions, and gives a good agreement with experiment and overall CFD, 3D CFD. Okay. And that brings us to the next poll we have, which is, how do you currently evaluate turbo machinery design performance? So I think David opens that up. Yep, the polls are incoming. And yeah, there are various methods, 1D, 2D, 3D, depending on the complexity you would like to use. Everything comes with an up and down, right? 3D CFD usually takes longer because you have all that, more information, or a combination of 1D, 2D, and then get the validated results from 3D CFD. That's basically what we present today. So yeah, as we see, actually a combination of 1D, 2D, and 3D CFD methods. So it's exactly what we present today. And yeah, it gives a good, my opinion, a good way on getting the first initial geometry in the 1D, 2D, and then you can finally evaluate and validate in 3D CFD and can iterate between those two.
Awesome. So go ahead and turn it back over to go to Sasha again. I'm going to have you share your screen.
Okay, you should see my screen. Please, David, let me know if it's not shown.
Looks good from my end, Sasha.
Okay, perfect. Thank you. All right, what I want to do now is I will want to give you a short demonstration of ArcStream flow path. I showed you the slides, but I also want to give you a short demonstration, on time, in real time, what we can do within ArcStream flow path. So we start with the generative designs of the preliminary design module, where I said we have a table of input parameters, boundary conditions, as we can see here. They're all based on the slides we saw in the beginning, which David provided for the current requirements of that fan we want to design. We can then say how many possible combination of these input parameters should be generated. I will set here a number of 2000. And what the solver is doing now, it will test various combinations of these input parameters and creates geometries and will analyze or check if these are proper geometries. So you can see here we have one meridional view of the best found geometry at this point. And each of these dots is a different geometry. We can analyze right here in the meridional view. We can see the 3D view as well if you would like to, as well as velocity triangles as well. So you might say, okay, I have all these points now. What I'm going to do to find my optimal? For that, we can apply some filters and also can change the axes on here. Because right now we see the flow coefficient and work coefficient. But I want to look at the hub diameter, for example. You can see here, as an example, the red dots are displaying, or the dot color is displaying the efficiency. And we can see if we would select the lower hub diameter, we will get more efficient design. it's just an example how you can use this tool to narrow down your search or expand the design space and see where your optimal and best design would be. Additionally, we can also apply filters. So here I can say, like, I want to filter my power output of my fan, or my power needed for this fan, to make sure that I hit the requirements which we set in the beginning. So here you can say, see I set these ranges here, and I also could say I'm not interested in any designs lower than, with an efficiency lower than 90%. So I could do here as well. You'll see all these gray dots are filtered out. I can hide these and then can, actually just look at the design space which is of interest for me. So I said that we can then look at the final selected design here. And the next step is, after we filtered the designs and have chosen the proper initial geometry, we go ahead into the 1D, 2D streamline calculation. Here we can run the various off design conditions. You can see here I can change my RPM value or my mass rate. So right now I would run this case. I can change this value and can run the new operating point, for example. Here I can say then if I want to run simply mean-line calculations or streamline calculations to include more sections. You can see these lines here. So it's up to you and how much or how accurate you want the results to be. And as well, as I've shown you on the slides, we can have a look at the various contour plots. You see here the Mach number, but also pressure distribution and temperature, and gives you a first insight in how the flow field would look like. Okay, so the next thing is then further down the road would be the profiler to then adjust the found geometry, because it just gives you an initial geometry and fine-tuning to accommodate for off-design conditions will be necessary. And here in the profiler, you can see the various characteristics on each profile section. So all inlet angle, outlet angle, stagger, you name it, it can all be found here and then can be changed. There are various features which allow you to change the geometry as well, profile. You can see updates right away. We see here the Mach number distribution on that profile, and you were able to see that it updated as soon as I did some changes here. As well as mentioned earlier, we can apply some smoothing techniques here. I can, for example, say do this in a linear matter, for example. I just do it as an example. And we are currently looking at the outlet metal angle. And I can change this, what I want to plot here, to the various options I have here. Right now, as I said, metal outlet angle, wedge angle, stagger angle, and so on can be plotted here. And I can also apply then some smoothing techniques to these sections as well. So more than that, we can also do sweep, boat, lean blade structures as well. It can be all implemented here. And you do that for all the various sections you have in your project or for that given geometry. So then the final geometry we have for this webinar is a swept blade we can see here. That is something then David will show in Star CCM Plus. And this is then coming after the profile and adjusting the geometry. We can use this then by exporting, as I mentioned, to the various formats, IGS step files, and so on. But before we go into that, I also want to show you the mapping tool, where we can, as I said, use it as a performance calculation tool. As you can see here, I selected master rate, RPM, and I'm interested in the power and pressure ratio for this turbo machine. But the second option I set is a parametric study tool. I can, for example, look at the restagger. So I can change my stagger angle in a way to make sure that I always have the proper stagger angle position for certain stators, IGVs, etc. So if I run this as is, we can see the results coming in here. You see it's pretty fast in creating the various speed lines. We see the results here also incoming in the various tabs. I don't want to go into too much detail here, but we see that we can generate performance maps in a very fast manner here, and can get the first insight into our geometry and how it will perform in off-design conditions. So now with that, I have now my geometry adjusted. I have applied some lean and sweep, etc., and would like to go into 3D CFD analyses and see how much the 1D or 2D calculation match with 3D CFD. So at this point, I will give over the scepter to David again, and he will talk about the Star CCM Plus section of this webinar.
Thank you very much, Sasha. That was great. All right. So yeah, thank you very much for that demo, Sasha. And before we jump into talking about Star, can we go ahead and we'll do our second to last poll here, which we are looking at, what type of solution, if you're currently doing 3D CFD analysis in your workflow, what's the primary tool you're using? Do you have a need for one? We'd love to hear about that to see if maybe we can help you out and maybe help you out with your process. That's really what we're here for today. Looks like a majority of people are using a commercial solution. There are a lot of academic and open source solutions out there as well that can be helpful, but it sounds like most of you are currently using a commercial solution. All right, so let's talk about Star CCM Plus. We've gotten our geometry out of AxStream here, as Sasha has done the preliminary design in AxStream. And in this case, what we'll show today is where we've imported StepCAD, and actually in this case it's the solid geometry of the blade and the stator, and we also have a hub and shroud surface. And what I'll show today is that we have some nice tools to be able to prepare turbomachinery geometry for CFD analysis right in Star CCM Plus. Importing a step file with the solid geometry isn't the only format. We can also do curve imports as well. You could import the actual CFD domain as well if you want, if that's applicable for your application. The other thing we can do in StarCAD is do something where we can actually parameterize the shroud line, so that we maybe want to do sensitivity studies and really understand some detailed results on how our shroud line cut affects our performance. Another thing we have in Star for turbomachinery analysis is being able to parameterize our simulation. And what I'm actually going to show today is a template workflow that you can be used to set up what you need to in Star CCM. So mainly using for boundary conditions, geometry, etc. But also we have tools to be able to parameterize the flow path for post-processing our geometry. In this case, we can see that we've done an axisymmetric parameterization of the flow path and able to do normalized span-wise locations to be able to post-process and review results at different span-wise locations, meridional locations, etc. Star CCM now has a hexahedral automatic mesher for axial turbomachinery. It also can be parallelized if you're doing multiple stages, so it can be extremely fast. We can use hex or tri elements to mesh the tip gap. Version 24.02 was just released a couple days ago, and that further improves this workflow and provides even smoother, nice streamlined meshes along the blade, and also now supports fillets at the blade root or at the stator shroud and hub as well. And what we'll see here is that when we create these automatic meshes, there's very minimal user input required. It's very tailored towards turbo machinery. As well as post-processing, once we run our simulation, we can get reports. I've done some custom reports to be able to look at our data versus the AxStream data and interrogate that to gain insights. We can create blade loading plots and have those automatically change with span-wise location. Do velocity plots or average velocity plots at certain meridianal locations in the flow path. That's automatically done using that parameterization approach. We can see streamlines, we'll show that as well. We also can do a 2D projection of our data, to be able to see, if we have particularly very curved surfaces or something like that, and we want to be able to see that in a 2D projection and unwrap that, we can do that as well in StarCCM. And then finally, we also have the option to do look at our axial flow essentially in our flow path using a circumferential averaging tool as well. So let's go ahead and jump into the software. We'll go ahead and open up Star here. And we can see here right away that I'm in my geometry that's been imported from AxStream. But let's say we were doing this from a templated workflow standpoint. And one thing that StarCCM has now is this thing called Simulation Guide. So for this templated workflow or this template file that I've created, and you can do this with anything you want in Star in terms of making a template for a project. Essentially what I did is I did my first analysis and then created a template from it. And then you can use that later on downstream when you want to analyze a new geometry where you make a new file and you open this as a template. And what we have here is this nice simulation guide here, which lays out all of the steps for this templated workflow. And it has these very nice things that you can add here where for each step you need to take in these instructions, you can actually add links to everything that needs to be done in the instructions, so you don't have to navigate through the simulation tree to find those items. You can just click on the links and it'll automatically take you to them. The other thing I have in my inputs here that I would use for a templated workflow in our parameters in our automation tree here, we can see here in the boundary conditions, if I click on that, I have a folder for boundary conditions where I have my rotor speed, my stagnation inlet conditions, or my my mass flow rate, or my initial inlet velocity. Depending on what type of boundary conditions I specify on my regions, it'll use these accordingly. If I use an inlet velocity boundary condition, it'll use the velocity condition. Likewise, a mass flow inlet condition, it would use the mass flow rate value. And this automatically changes depending on how you set it. In this case, we're using a stagnation inlet condition and a static pressure outlet condition. So all we have to do is set these for our boundary conditions, and these would come right from AxStream. I also have some geometric items in here where we can see I have these R values. And these R values are actually the same radius, mean line radius values that were used in AxStream for the 2D mean line analysis. The reason I put those in there is that these will automatically calculate many of the same values, and then you can interrogate those against AxStream as needed to find out where we can improve things, or maybe we need to adjust some loss coefficients or something like that to drill down on our design. So once we put that information in, bring our geometry in, we're good. So let's look at that geometry a little bit though. So if I go to my 3D CAD view, it comes in like this. It's a solid. We don't have our flow path yet or anything like that for CFD analysis. But one thing that's nice about this is once I have this set up as a template and I work in my 3D CAD environment, which is an extremely powerful tool in StarCCM, because the StarCCM CAD tool is extremely capable and very highly parametric to be able to do whether imported geometry that I'll show you here today, or creating your own geometry for maybe something else that's not turbo machinery. Or maybe in this case, you're adding a nacelle to the design or something like that. You can do your nacelle design all in here and then export it later for something else. So in my CAD, I have this CAD that I've imported here where I just have my hub, my shroud, and my blades. And in my features, we can see here I have this CAD import. And what's really nice about the Star CCM CAD environment is that if I have a different variant for this, I can re-import the new variant just by doing, an edit and then model re-import. Select the different file. I won't do it now because it would take a couple minutes for it to run through it. But essentially what it will do, it'll prompt me to match all of the different geometries and make sure that I'm matching the same blade face on the new imported geometry as the old geometry. Then if I do that, everything propagates to the end, and what I end up with is my final flow path geometry here. I'll hide this, which is these nice periodic regions. And these will be great for doing my nice automated hexahedral meshing in the Star CCM solver or mesh solver. The way Star also has a really nice tool for this, and it's called a turbo slicing surface. And I'll show that here. And essentially what this does is it allows you to create a nice average surface of your turbo machinery so that you can pattern these, in the correct angle that you need in order to create these nice periodic regions. And the way we set these up, I had to create a little bit of geometry for these, but basically you're selecting your primitives of your turbo machinery geometry, meaning your blade faces, trailing edge, leading edge, hub, shroud, inlets and outlets, and then it's automatically creating this. And this works for axial, radial machines, radial diffusers, and then with the newest release of Star CCM, it also works for mixed geometry as well. We also have a few, tools here to change kind of how sensitive this surface is depending on the shape of your turbo machinery geometry. So it makes it really easy to create these nice, clean, periodic regions. And this is what I would have going into Star for my geometry. I've also, in this CAD geometry, parameterized my shroud gap. And this is something that I can edit directly in the simulation portion of Star to do design studies and things like that to look at performance versus shroud gap. And maybe I need to do some iterations on that, depending on I have my blade vibrations and stress analysis to find out how big my shroud gap needs to be. And that's something we can update very quickly. So I have my 3D CAD. Let's go back to our simulation guide, go back to our simulation tree. So I have my CAD. I define my boundary conditions from AxStream. If I import a new geometry, I have my parts that come in here, but everything is tied and is completely tied back to my 3D geometry. And using these surfaces, I have on each one of the rotor and stator, which are just really the primitives of the turbo machinery geometry: hub, inlet, leading edge, pressure surface, suction surfaces, my periodic regions. Just go to my geometry here. We can see our periodic regions. So, I'll set up my periodic interfaces in Star CCM for each one of these. But this all flows back down through. I don't have to do any rework on this when I import a new variant. And then I've tested this with a couple of different variants. And this happens on the rotor and the stator. Likewise, this flows down directly to my operations in this case, which are my turbo machinery mesher for my rotor and my stator. And so once again, I'm using those primitive turbo machinery surfaces in this case to set that up, and then these are automatically executed. The controls I have here, though, are perfect and tailored towards turbo machinery, where I can set the number of intervals that I have, in the blade direction, axially, how many I have in the span-wise direction, so how many divisions I have in the span-wise direction. Also, in this case, this is the rotor. I can set how many intervals I want in my tip gap, my near wall thicknesses for hitting my Y plus of 1. This is all stuff that's tailored to be able to do quickly and efficiently. And we can see what that looks like here after I'm done. Another thing we'll see here is this parameterization. But in my mesh, we can see here, I can just hide that. And we can see my nice, clean, turbo machinery mesh where it's meshed my tip gap for me and everything accordingly. In this case, because there's some fairly complex shapes here and I wanted to get a nice clean wrap around here, I used tries at the tip. So it's a combination of tries and a hexahedrals in this case. So I have a nice mesh. This mesh is about 8 million cells total. This is a pretty, very, very fine mesh for this case that's mesh converged and done some iterations on it. What else do we want to show next? So we've run this. One other thing that we would need to set up in this is that parameterization we talked about, and that's set in our tools. And if I go ahead and go down to my parameterizations, we can see I have this axisymmetric parameterization, and this allows us to normalize the geometry for post-processing. So being able to view contours at different percent blade spans, different percent meridional directions, all of that. And once again, these are really easy to set up because we're just identifying our meridional locations, so our inlets and outlets and our interfaces, the span-wise locations at the min-max, so the hub and shroud, and then our periodics and the circumferential directions, and then star CCM is automatically normalizing this geometry for us. And we can see that in this same scene that I just showed, where we can confirm that this normalization is correct because we can view it here, where we can see that I'm viewing the axisymmetric span-wise coordinate, where it just goes from 0 at the hub to 1 at the shroud, and then likewise for every stage that you have, for the rotor, the outlet of the rotor is at a value of 1, and then the outlet of the stator is at a value of 2, and the inlet is at a value of 0. So this comes in really handy when it comes to doing our post-processing. We can see that here, where I have this nice contour plot at a span-wise location of 80% blade span. And we also do that, for our projected, span-wise location. The nice thing about this, though, in this setup is that this is all parameterized, and I can change this. If I go into my parameters in this post, I have a parameter here for M bar and S bar, which essentially stands for the normalized meridional direction and the normalized span-wise location. And as I change this, I just challenge this, maybe I want to go back to 50% blade span. In this case, if I enter that, it automatically updates all of my views for that, because all of these are controlled using that span-wise location value. Likewise, that works for the stream-wise direction in the meridional direction. In this case, I'm at a stream of 1.5, which is halfway through the stator location. So talking a little bit more about post-processing. So we saw the projected view. Then once again, it all automatically comes from that parameterization tool. We can view our streamlines, by creating, derived streamline plots like you would for any other simulation in STAR. We can also expand this to 360-degree geometry that you see here. So that parameterization tool also makes it possible to do that. And if I go ahead and open up my streamline tool here, there's actually an option to just say how many instances of the geometry I want to show. Some other really nice post-processing features that are tied all automatically into this template are like this velocity profile view, where we can see all of the velocity instances at a streamlined location, and then also an average of those at that streamlined location to view the average velocity profile at each location if we would like to, and this is all automatically done with this template. Likewise, blade loading for the rotor, and as well as blade loading for the stator. And once again, these are all tied to our automation here, or our parameters, where if I change this value, to 0.1, it automatically updates that for us, and we can see that. Next thing we have is our reports for post-processing. So as I said, I did some geometry inputs for this to be able to do some really nice reports, and this is all contained within this template. So if I go to my reports, I have mass flow average values for my kinematics, my thermodynamics, all, many of which would be shown in ActStream. So I can create, run these reports where I want to see, my tangential velocity, mass flow average tangential velocity, and I can see that, at all of the axial locations here. And then I also maybe want to look at these at different streamlines, and maybe those same streamlines that were done in ActStream. And these are all set up in here where I can do these span-wise averages, where I've done, done some of the use the really nice math operation tools that are available in StarCCM to create these. And it didn't take a terrible amount of time to create these by just using these expression definitions. So in this case, maybe I want to see, c theta, which is our tangential velocity at each one of those streamwise locations. So, all of those R value locations, I can see those, and I can see it at each, inlet and outlet of each region for the rotor and the stator as well. So I have a really rich output here to be able to look at my results. And then we've run all those. One thing I'll show too as well, we can see here, I wanted to mention this. We can see there are our periodic geometry here. And if I bring my actual meshed geometry right next to it, probably not going to let me do that. Oh, there we go. I bring that over, and then I show my mesh here. One of the things that Star does that's very powerful and nice for meshing is we can see that the final mesh geometry is actually different than what we input slightly. So Star will actually further optimize this geometry to create even cleaner periodic regions as it does the mesh. So that's another really nice thing. And this automatically, once again, is updated. So really all we have to do is, to recap, we bring in our geometry, we add our boundary condition values, and add some geometric values. Maybe if we want to interrogate against our geometry tool, and then we run this and we're ready to go, and we're ready for post processing. So we can create some really fast automated workflows with this, and it's not just for this case. This could be done for any type of turbo machinery. Siemens has a specific one that's already set up for axial turbines. That's extremely powerful. That can be done using curved geometry, whatever, and is highly automated. So with that, just go ahead and jump back to our slides here. This certainly wouldn't be the end of our simulation and studies in StarCCM for this type of application. We would certainly want to go on to looking at things like aeromechanics and aeroacoustics. Aeroacoustics being extremely important, especially for a lot of these applications of these ducted electric fans are designed to be used in urban areas and in highly populated areas where noise is definitely a big deal. So being able to accurately evaluate that is critical to meet those constraints. And this can be done. You don't have to do this necessarily with a full transient solver. Believe it or not, we can use the harmonic balance solver in StarCCM to evaluate aeromechanics as well as aeroacoustics. And this is done in a modal solution fashion instead of using a full transient fashion or full transient solver, but we end up with transient time domain results as a result of that solution. We can also do work on electromagnetics and Star, would certainly be important for motor design. We also might want to look at optimizing things. Certainly a nacelle design would be important for this. Nacelle effects, certainly different angles of attack, things like that would be critical to performance for this type of application. Also looking at motor cooling. These motors are usually generally extremely power dense and do require some cooling. So maybe we need to design some bleed air, or some ram air cooling or something like that for these, or maybe even liquid cooling applications with a radiator, depending on what we need to do. And as I said, nacelle design and analysis. And I show a couple plots here. Make sure I'm actually going into the slideshow, but we can see that here. where this is a harmonic balance analysis here, where we're getting transient type results from a frequency domain solution, which is it's much faster than running a full transient solution, but we get the transient results. And then the other graphic I have here is actually a scale resolve solution done for aeroacoustics analysis as well. So with that concludes my STAR CCM portion of our talk today. Concluding that, we'll say, what we've read over today, we really want to utilize AxStream in this case to obtain our overall initial designs, look at our geometry modifications, be able to iterate on that, and get really our first insight into performance. And then likewise downstream, we use that to obtain our full 3D flow structure, our 3D streamlines, and our final insight into performance. And really, what we've shown today is that you can use these two tools together in conjunction to, establish a very efficient workflow. We can get our best design, we can optimize it, we can do it quickly, we don't have to do lots of rework. And that's really what we're targeting here is like, let's iterate through our designs, let's get a good design and not need to do a bunch of rework and make mistakes where, we're having something in a prototype that we need to go back and retool. So reduce costs, reduce time to market is really our goal here. So with that, our final poll question is really, if we can tell you more about this, we would love to know how. Whether or not we do a one-on-one meeting with you, some type of technology benchmark. We would offer training and software evaluations at Maya as well, whether it's custom training or Siemens, on-demand training. We can help with that as well. And of course, we're a value-added reseller of STAR CCM here at Maya, and then of course, Softonway is your go-to for their AxStream software in this case. And we really thank you for joining us today, and we'd love to hear any questions. So it looks like I have here, does STAR CCM version 24.02 support radial turbo machinery blades? So you can do radial turbo machinery blades in STAR CCM. We don't have the fully automated turbo machinery mesher available for radial turbo machinery blades. But we can use other meshing algorithms to evaluate radial turbo machinery, and we have customers that do that. I have another question here that says, which theory is used to design the ducted fan? In this case, we're using general turbo machinery, equations, and in the STAR CCM, or excuse me, say the AxStream suite, for doing this. Whether it's, we're looking at our velocity triangles, all of that, and it's really the basis of all these designs. And then looks like we have another question here. Bring it up. Let's see. Another question here, Sasha, that says, how are losses taken into account in the 2D calculation? Do you think you could answer that?
Oh, yeah, definitely. Yeah, so the losses in AxStream are taken into account through various loss models. So for the fans, for example, there are loss models made by Leapline, for example, but you also can bring your own. If you have your own company-wide loss models you would like to use, they can be established as well. But by default, there are well-established literature references used for calculating the losses.
Yeah. All right. So it looks like we have another question here. So in STAR CCM, so someone's asking about like a propulsion workflow rather than a turbo machinery perspective. One thing that we've shown here today that Sasha showed is the generation of the maps. So using those for a system level or propulsion performance level analysis. could be used in some type of 1D simulation tool, so that you could definitely leverage those in that regard. You know, and also maybe once you get your thrust coefficients and things like that from your CFD analysis. I didn't specifically cover all of the, you know, the outputs of our post-processing here, but thrust is one of them. And so, you know, that's something that could definitely, you know, you use for that later on down the road for a more system level analysis. And I have one here. Anyone on this list you want to take, Sasha?
Let me see.
See one here that says no ducts were shown today in our design case. Certainly, you know, the duct is a big piece of this. Today we're focusing mainly on the turbo machinery section, but as I mentioned in Star CCM, you would definitely, we want to expand this to, you know, a system level analysis where you would be looking at, you know, maybe angles of attack, designing your duct, the drag coefficient of your duct. This would also come into play too from an acoustics perspective as well, where you want to make sure you're not, you know, amplifying the acoustics with your duct or something like that. Those are all things that can be done in Star CCM.
Now I'd like to add for the ArcStream portion, you can define or generate the various ducts in for the internal flow, but the outside is not considered inside ArcStream, because ArcStream considers the internal aerodynamics of these machines. So you could be using ArcStream to adjust the flow path and everything, but how the duct overall on the outside looks like, that is something you would do with Star CCM Plus.
Yep. And then I see another question here. Can you use Star CCM to do the consecutive stages design? So yes, you can. You can do, you know, as many stages as you would like in there, where you can, you know, if you were doing a multi-stage axial compressor, multi-stage axial turbine, or even, you know, multi-stage, you know, radial geometry, those are things that you can add and do in Star CCM Plus, especially that, you know, especially leverage the axial designs very, very well.
Yes, and I also just would like to add, I mean, the question was about CCM, Star CCM Plus, but in ArcStream you also can do multi-stage machines, right, and then can export that geometry to Star CCM Plus as well. So there's the same workflow essentially established there. Just wanted to mention that since today we only talked about one stage fan. Yeah.
Okay. All right. All right. So that, you know, our last poll here saying, you know, it looks like most people will, you know, like training and evaluation, certainly, and also, you know, reach out to us. You want to meet, we're happy to share more if you have any other questions. And that's what we're here for. Our final contact information here is on our last slide. You can reach out to myself or Sasha, and if it's not a question we can answer, or you're looking for help in another space in any of our products, you know, whether it's SoftWay or Maya, we're happy to find the right person for you. Or if you're just, you know, solving a problem that or you have a problem that you're not quite sure where to go with, we're helpful with that too as well. So with that, I think we will go ahead and conclude for today. There was a lot of questions. If we didn't get to your question, we can go ahead and follow up with you. And with that, we thank you and enjoy the rest of your day.
Thank you also from my side.